Hi, welcome to 6.1. Today we're going to be talking about radian and degree measures of angles. So the first thing to talk about is the unit circle. Now a unit circle is a circle with a single unit as the radius. The radius is 1. Could be 1 inch, could be 1 foot, could be a mile, could be 1 centimeter. But the point is it's just 1 unit. And that's what we're going to be talking about here and comparing these or developing these concepts. So a radian measure. Now I want you to notice the word radian. Looks like radius, and that actually is part of the definition. A radian measure, in radian measure let theta, this looks like a circle with a line through it, that's the Greek letter for theta, be an angle at the center of a circle of radius 1. So here's our theta at the center of the circle with radius 1. That's the unit circle, as shown in this diagram. The measure of theta in radians, abbreviated as rad, and if you look in your calculator, the TA89, the TA83, the TA84, they all have the option to go into radian measure. So RAD stands for radians, is the length of that portion of the circle subtended by theta, that is the portion of the circumference included in the angle. So let's take a look here. Here's our radius. So if we just took that measurement off and wrapped it along here, it might have, you know, 1 radius to that point. And then what's this, maybe 0.5 radius? So this whole thing may be like 1.5 radii or 1.5 radians. So that's a way to think about a measure of an angle. Instead of the degree that you may have seen before, this is in terms of how many of these radii are there. So note that the unit length of measurement is immaterial. You know, people are used to inches, feet, miles, so that doesn't really matter so much as long as the circle has a radius of 1 unit. The length of the subtended portion of the circle in the same units is defined to be the radian measure. So this angle would be 1 radius, 0.5 radius, 1.5 radians. Okay, let's talk about the definition of an angle. An angle, classic definition of an angle, is 2 rays, R1 and R2 in this case, sharing a common point of origin. So here's your common point of origin. So the initial side is R1 in this case. And the terminal side is R2. That means it starts at R1 and goes to R2. This is the terminal side. Now in this case, there's a typo here. If you were printing these notes, you want to correct this. This angle, because it's going this direction, would typically be measured as a negative angle, where theta is less than 0 because it goes that direction. Going in the counterclockwise direction is positive. Going in the clockwise direction is negative, and so that also needs to be corrected here. A positive measure is the value of theta when defined by a counterclockwise rotation from the initial side to the terminal side. A negative measure is the value of theta when defined by this one's the clockwise one. So let's correct that in our notes here. Rotation from the initial to the terminal. So in this type of thing here, this would be a positive one. So this is the case where theta is greater than 0. Okay, so going in that counterclockwise direction, that's a positive measurement. Now we talked about the unit circle. That's a circle of radius 1. In order to use our definition of radian to measure an angle defined by 2 rays, we place the vertex of the angle at the center of the unit circle and measure the length of the arc between the initial and terminal sides. So standard position is an angle with its vertex located at the origin of the Cartesian plane and its initial side along the positive x-axis. So the unit circle would have a graph of x squared plus y squared equals 1. Here's an example of a unit circle, and here's an angle. So you can start here at the terminal side, or sorry, the initial side, and that corresponds with the positive x-axis. The origin is where you have the vertex of your angle. So here, if you went this direction, that's going to be negative, and if you went around this way, you'd have, let's call it something else besides theta. Maybe theta prime would be positive. But we could take our angles and put them on the unit circle, and then we could discuss them in radian measures. How much of the radius is this angle? How much of the radius is this angle? Now we're going to talk about the conversion between degrees and radians. Now, the circumference of a circle is 2 pi r. Now, if r equals 1, because we're talking about unit circles, then c equals just 2 pi, because 2 times pi times 1 is 2 pi. So in degrees, one complete circle is 360 degrees. So the following conclusions can be drawn. 360 degrees is 2 pi radians, whereas 180 degrees would then be pi radians, and 90 degrees is pi over 2 radians. See that relationship? Dividing by 2, you get 180 and pi. Dividing by 2, again, 90 and pi over 2. So our conversion formula is the following. Since 180 degrees is pi radians, we know that 1 degree is pi over 180 radians, and the 180 over pi degrees is 1 radian. Now typically when we're going to do conversions, we'll have pi in there so it'll cancel out, but if not, you can just do your approximation for pi, like 3.14. You can go further than that. Our calculators have pi built into them. So multiplying both sides of these equations by an arbitrary quantity of x, we have x degrees would be x times pi over 180. That gives us radians. If we have x in radians, we do x times 180 over pi, and that gives us degrees. So let's do some problems here. Okay, convert 2 degrees. Negative 7 pi over 6. Want to go to degrees. So we're going to multiply this by 180 degrees over pi. Now notice I have pi on top and pi on bottom. I also have 6 down below. So I can reduce 6 with 180. That leaves 30 degrees. So negative 7 times 30 is negative 210 degrees. So that was converting that to degrees. Let's do the next one, 7 pi over 20. So I'm going to multiply again by 180 over pi. Right off, those pi's divide out. 20 goes into 180 9 times. 7 times 9, and this is in degrees. 7 times 9 is 63 degrees. Now we're going to convert to radians, 93 degrees, and multiply this by pi over 180 degrees. So notice here we have degrees on top, degrees on bottom. So the degrees cancel out. Okay, this one's not a real pretty one. Let's see what we can get out of this. I could divide the top and bottom by 3. Let's see if we can go more than that. If I divide this by 3, I have 60 down below. And divide this by 3, it looks like I have 31 degrees above. In radians, it would be 31 pi over 60. Let's verify this for a second. Yeah, that's the best we can do there. And if you want that in radian format, you're at 1.62316 radians. You can get that from your calculator. And the last one of this set, we're going to convert 120 degrees into radians. So we're going to do the conversion, pi over 180. Again, we want to get rid of degrees, so we have degrees down below. So 120 and 180. We can divide 60 out of both of those, and we're left with 2 on top, 3 down below. It's 2 pi over 3, and that's kind of a standard value. We'll leave it like that. Say radians here, though. Okay. Now, commonly encountered angles, let me scroll this up here. "30 degrees is pi over 6. These are things you want to memorize. I mean, I still have students in my calculus class, and I say, okay, what's pi over 6? And they're like, I'm not sure. I say, what's cosine of pi over 6? And we'll be getting to that. But these are things you want to memorize. 30 degrees is pi over 6. 45 degrees is pi over 4. 60 degrees is pi over 3. And you could do the conversions, but after a while you'll start seeing a pattern. 90 degrees is pi over 2. So note when the degrees symbol is absent, that means we're in radian measure. Okay, so use the information in the diagram to determine the radian measure of the indicated angle. And this is a unit circle. Which means we have radius 1. And this point here, this is negative 5, negative 0.5. That means we're at negative 1 down there. We're at 1 here. We're at 1 up here. And we're at negative 1 over there. So the question is, what would this angle here be? What is this theta going to be? Well, if this is negative 0.5, that means this side here is negative 0.5. This side here is 1. We want this side over there. We'll call that A. Now, by the Pythagorean theorem, we know that A squared plus negative 0.5 squared equals 1 squared. The sum of the squares is the side, the square of the hypotenuse. So A squared plus 0.25 equals 1. If we subtract 0.25, A squared is equal to 0.75. So A is equal to the square root of 0.75. Now, this is the principal square root is positive, but we have to go with plus or minus because of the variable. And given the location here, we're on the x-axis to the right of the origin, so it needs to be the negative 1. So A equals the negative square root of 0.75. Well, let's take that a step further. A is negative the square root of 3/4. So A is negative square root of 3 over square root of 4. And A is negative square root of 3 over 2. So that means this side up here is negative square root of 3 over 2. And this side here, it's negative 0.5. You can also think of that as negative 1/2. Now let me tell you about something about triangles. There are some special triangles. And some of you may have dealt with this if you've had a geometry class before. And one's called a 30, 60, 30 degree, 60 degree, 90 degree triangle. In a 30, 60, 90 degree triangle, the relationship between the sides is this. Side ratios are this. The side opposite the smallest angle is 1/2. The side opposite the middle angle is square root of 3 over 2. And I don't want to do that dash because it looks like a minus, maybe a comma. And the side opposite the biggest angle is 1. That's the ratio of the sides. So this, using this knowledge now that I've shared with you, this angle here, do it this color, the side opposite is 1/2. We have a square root of 3 over 2. We have a 1/2. We have the 1. We have all the components to fill this in. So the 1/2 is the side opposite the angle that we're talking about. So it must be the 30 degrees. So this angle is 30 degrees. Now, I'm not finished with this problem yet because we want to know this given angle. What's that one going to be? And there's a red pen down here. I want to make this notation. If you went from this point around to here, that's half of the circle. That's half of 360. That's 180 degrees. Same thing if you went this direction, that's the other half. That's the other 180 degrees. So we've traveled 180 degrees, but we're 30 degrees short of that. So it's 150 degrees. But there's one last part to this. Because we traveled in a in the clockwise rotation, this is the negative direction. So we would have to say that theta equals negative 150 degrees. Excuse me, in clockwise direction. And so because we went in the clockwise direction, that's why it's a negative 150. So this theta is negative 150. Let's talk a little bit more about those triangles, the special triangles. And this is from the textbook. Let me clear the board a little bit. From pages 459 460, you can read about this, the ratio of the sides of the following triangles. You can see the illustration here. 30, 60, 90, as we just discussed, that would be in radian mode, pi over 6, pi over 3, pi over 2, and the ratio is 1, square root of 3, and 2. In the last problem, I was talking about 1/2, square root of 3 over 2, and 1. If you divided each of these by 2, you would have these values. So the ratio still holds. Likewise, a 45, 45, 90 in degrees would be a pi over 4, pi over 4, pi over 2. By the way, these aren't negatives, these are just dashes between them. Pi over 4 corresponds to 45. Pi over 2 corresponds to 90. This would be a 1, 1 square root of 2 ratio. Or you may have seen this as 1/2. Well, you may have seen this, everything divided by square root of 2. So think of it as 1 over the square root of 2 times square root of 2 over 2. Square root of 2 over square root of 2 is square root of 2 over 2. That would be the rationalized denominator form. So you could have seen this as square root of 2 over 2, square root of 2 over 2, 1. That's another way you may have seen this in the past. And just to give you a visual on these, it's not perfect, but I think you'll get the idea here. This is the smallest angle up here. That'd be our 30 degrees, 60 degrees, and that's a right angle. That's 90 degrees. So the ratios would be 1, according to this, square root of 3, and 2. Whereas in the second case, we're talking about 45 degrees, and there's your 90-degree angle. And so this was showing the ratios of 1, 1, square root of 2. I do want to stress, though, that this ratio is the same as that. We just divided every term by square root of 2. Now, our next concept is that of, we're going to talk about arc length and angular speed. So arc length formula. So given a circle of radius r, so this is not necessarily a unit circle, it could be r. The length s of the arc subtended by a central angle theta is s equals theta over 2 pi times 2 pi r. So this gives us the fraction of the circle we're talking about times the circumference. But if you reduce out here the 2 and the pi, you have theta times r, or r theta. Okay, given a circle of radius 22.5 centimeters, find the length of the arc subtended by a central angle of 3 pi. Okay, so circle. Our radius is 22.5 centimeters. Now, we talked before that 2 pi was 1 full time around. Go around a complete time, that's 2 pi. We're going 3 pi, so that's 1 time further. So what we're talking about is 1.5 times around. So our arc length is r times theta, which is 22.5 times 3 pi. And this was in centimeters here, of course, and 3 pi is in radians. So what do we have? 67.5 pi centimeter radians. That's our arc length. Next one, I probably should scroll up a little bit, give myself more space. Given that two cities on the equator are 100 miles apart and have the same latitude, that is, one is due west of the other, what is the difference in their longitudes? So use a value of 3,960 miles for the radius of the Earth. So think about this. Here's the Earth. We sliced it in half, and so this is the equator. We have a city. I'm going to exaggerate this because 100 miles will not look like much on the globe. So here's the city, and let's say here's the city, so that they're 100 miles apart. So what we're really after, this is 3,960 miles. 3,960 miles. That's important because this is in miles down here too. What is this theta going to be? Well, S equals r theta. S is, in this case, is the arc length. In this case, it's 100. So S is 100. R is 3,960 miles. So 100 equals 3,960. Let me include my units here. 100 miles equals 3,960 miles times theta. Then we're going to divide by 3,960 miles. miles cancel, and this should have been miles times mile radians. 3,960s cancel. And what are we left with? Theta equals 0.025253 radians. So if we take that 0.025253 radians and convert it back to degrees, multiply by 180 degrees over pi radians, we have 1.44686 degrees, and it can go to 1.45 degrees difference in longitude. Or is that latitude? Longitude, yeah. Okay, that's it. So let me just recap. This one uses arc length is r times theta. We know the arc length, that's the 100 miles apart. We know the radius, that's 3,960. We don't know the angle. We want to find the angle. Plug in the pieces and do our division. Our next concept here is angular speed and linear speed. If an object moves along an arc of a circle defined by a central angle theta in time t, the object is said to have an angular speed of omega. This is the Greek letter for omega. I believe it's a lowercase version. Given by omega is theta divided by time, so the angle covered divided by the time it takes. If the circle has a radius of r, the distance traveled in time t is the arc length s, and the linear speed v is given by v equals s over t, but s was r theta over t, which is r times omega. So, the Earth takes roughly 23 hours and 56 minutes to rotate once about its axis. This is why we have leap years, because it's not 24 hours. Using a radius for the Earth of 3,960 miles, what is the linear speed in miles per hour relative to the center of the Earth of a person standing on the equator? So ignore, for the purpose of this problem, such motion as rotation of the Earth around the Sun. We're just talking about the spin of the Earth. So again, here's our look at the Earth, the equator. Here's our radius of 3,960 miles. So our velocity is r theta over t. The radius is 3,960 times our theta. It's a full rotation, 2 pi, divided by 23 hours and 56 minutes. Well, 56 minutes would be 56 over 60. Let me just do this conversion. Times, how should I say this? 1 hour over 60 minutes. So the minutes would cancel. That gives us 56 over 60 hours. That fraction of hours. So 23 hours, 23 and 56 60th of an hour. And if you put that in the calculator, we're going to get 1,039.61 miles per hour. Just standing on the equator. So we're, unless you were watching this from the equator, we're quite a bit north of that, so we're not going quite as fast. Our next topic is area of a circular sector. So what is a sector? I like to think of a sector as a piece of pie. Get a Out of a circle, you can take that piece of pie out or piece of pizza. That's the sector. So the sector is the portion of a circle between two radii. So if we're talking about here's a radius, 2 radii. This would be a sector. So, sector area formula, it's really not as bad as you might think. The area of a sector with a central angle of theta, in a circle of radius r area is theta over 2 pi. So theta is the part of the circle we're talking about, 2 pi is the entire circle. So we're talking about the portion of the circle that we're dealing with times pi r squared. Well, the pi's cancel, and you're left with r squared theta over 2. R squared theta over 2. So that would be the area of a sector. And that's where theta is in radians. So our last example for this section. Find the area of a sector of a circle of radius 3.5 feet with a central angle of 27 degrees. So what is this area of this part going to be? Well, the formula we have is in radians, so we're going to have to convert 27 degrees to radians. So 27 degrees times pi over 180 degrees. That's going to be 3 pi over 20, and that's our radians. So the area is r squared theta over 2. So the area is going to be 3.5 squared times 3 pi over 20 all over 2. What do we get from that? 2.886 square feet. Okay, and that is the end of 6.1.